Hi, in this video, I'm going to make a brief summary of the Mojo language user manual from the perspective of syntax and semantics. Mojo is a relatively new language developed by Chris Ladner, the developer of LLVM, MLIR, and other projects. And the goal of this language is make Python efficient. Python is probably the best language for artificial intelligence, but the flexibility, the easiness of use has its price in efficiency. It's not strict in typing. Everything is dynamic, so that's gonna take a huge overhead, and it might be impossible to make it efficient. So what Chris Nander and his team did in Modular was making a superset of Python that allows to have additional constructs similar to C++ to make it efficient. So the user can gradually be more like C++ or more like Python, depending on the situation. And under the hood, they use MLIR, which is a multi-level intermediate representation with different abstractions, different dialects. For example, linear algebra dialect, affine dialect, and other dialects that allowed optimizations at the right level of abstraction, and it gradually lowers into LLVM. So basically, they, with their framework, Magic Max, showing the left, upper left, they can have significant speedups over TensorFlow, PyTorch, and things like that. So if you're looking for efficiency, this could be an option for research for a language. So they also, with the help of MLIR, they optimize for multiple targets. So that's something very useful of this language. This video is going to be more useful for you if you are familiar with Python and C++. So let's go ahead to take a look at the manual. As I mentioned, Mojo aims to be a superset of Python, but they're not quite there. They don't have classes, they don't have comprehensions and other things, but that's their goal. But in the meantime, they have interoperability with Python and C++. So you can call Python from Mojo, although not vice versa, although that is coming soon according to the roadmap. You can see Mojo as the middle ground between Python and C++, and you can be in any extreme. They even have unsafe pointers in Mojo. But I like the name because the name itself of unsafe pointers discourages their use. You're not supposed to do it. There might be some string case which you might. So basically, it's like a Mojo language, like Chris Ladner says, is a gradual revelation of complexity or something like that. So it's like they're giving you a slide bar to allow the programmer to be in any point in between these two extremes. One extreme, it is a highly flexible, dynamic, easy to use, which is Python, and the other extreme is strict, is efficient, but it could be unsafe. So you can have a be in the in between. I like the way that the syntax of Mojo can offer the same efficiency as C++ while still being safe and easy to use. And we're gonna see that in a moment. And yeah, basically you can see, as I mentioned before, Mojo can be seen as a front end for MLIR. You can see, for example, some of there's a video Chris Snyder showing that the Boolean type is implemented calling MLIR directly, and people can do the same with their own dialects and things like that. There are two ways of defining function in Mojo. In the left, you have a Python-like, which is the def. You don't have to define types on the arguments. And then on the right, you have fn. This is the recommended if you want more efficient code. But then it forces you to declare types of the signature, and the variables are declared as var. And this is going to be more stricter in the scope, like C++. And you don't have to declare the type of this one because inside a function, if they're local, you can infer the type. So you don't need to do that. You can see here at a glance some of the features on Mojo. They have a metaprogramming, and you have traits that are useful in metaprogramming. For example, the type of the first one has to be a string, and this you have a list, a variadic list of strings. and everything has to be. So when you have stringable, it's a trait that the type has to meet. It could be an integer. That integer could be converted into a string, so it is stringable. So you can pass a list of a combination of strings, integers, and floats, whatever. And then you're gonna be able to convert it into a string like this and print it out. Print that out. Okay, let's go to next one. So yeah, you define variables like this. You don't have that in Python, and with that you can also specify the type, and they have a implicit conversion, explicit conversion, but once you define a type in Mojo, this is more strict than in Python. Everything is an object type. It's very inefficient. In here, it's going to infer the type, so it's an integer. Then I assign a string, and it's going to complain. Okay, so then Mojo has also late initialization. So, for example, if you define this variable and don't initialize it, then it's going to complain, and that's good for efficiency. Also, the variables are going to be more, if you have it like Python, for example, then this variable is going to point to this one, and you can override. You can see that the value is overwritten here. But then if you declare it like this locally, then this value is not the same as this one. This is something that Python didn't have. And you can see that the original value in the outer scope remains the same. Okay, they have a core, I don't know if I can call it built-in SIMD type, but it comes with Mojo. And it's basically it's a struct that is parameterized. In Python, in Mojo, metaprogramming is called parameters. They acknowledge in the documentation that it's confusing because in C++ and other language you understand parameters as the values that you pass in the I/O, the signature of a function. But here they refer to it as metaprogramming. So you can see this D type. This D type cannot be instantiated. It's like an enum, and determines the type for a type that you're creating. In this case, it's going to be a SIMD, which is a structure. And then you have these the values to initialize the SIMD vector, and then you can just apply dot product to it. And this is the number of elements that it has. So both of them are parameters for the template, for the metaprogramming. Okay, so you can see the aliases are good for defining types, and you can see that float32 is really a scalar and use these enum-like D types to determine the type. The same with int8. So all of those, you have int8, unsigned integer 8, all those classic primitive types are really structures like this. And they are scalar, of course, but the scalars notice there is a SIMD, so everything is derived from this one. So by doing this, you see the size 1 because a scalar only has one element. So by doing this, SIMD becomes core part of the language, of the Mojo language. So they put parallelization and vectorization at the forefront on the design of this language. Okay, so they have some classical list, dictionary, set, optional, and things like that. And they also have you're gonna see these a lot. These are decorators that basically is like they're like wrappers. And this one in particular is to indicate that this structure is passable in a register. So you have things in the heap, in the stack, but sometimes you can put it even in the register. It's even more efficient. And you can only do that with very simple structures like this one, scalars, things like that. Okay, I'm not going through a control flow because it's very obvious. It's similar to what you see in C++ or Python. Okay, so they don't have classes, but they have structures. And with the structures, you can create you can have the constructor, copy constructor, move constructor, destructor, all of that. They have all those lifecycle methods. And you can see that they have this double underscoring here. They call them Donder methods. And they do not have a inheritance in Mojo, but they do have traits. And traits, you can see traits as Java interfaces or concepts in C++. So basically, in terms of object-oriented programming, traits are like abstract classes with methods that are not implemented. So, and then if you inherit from those traits, then you have to, it's like a contract, you have to implement those methods. And we're going to see a little bit more later. So you can have static methods. So this is another decorator to indicate that this method is static. And yeah, they don't have a runtime dispatch like and runtime binding like Python, which is you with traits you don't need it. So traits are way more efficient than this. And structures are known at compile time. So this is a common trend in Mojo. They want to do everything at compile time, but at the same time being safe, being debuggable, easy to use. Okay, so they have this value decorator to automatically create the lifecycle methods, the donder methods for lifecycle management. So for example, in here, these are the three methods that it's going to create. The constructor, a copy constructor, and move. Yeah, those are the donder methods, and you can see you create the structure in here, and you can copy it to pool and print it. Okay, so these constructs, the following constructs are for memory management: the borrowed, in, out, on, and reference. They behave like a smart pointers in C++, but it's like the smart pointers in C++ become part of the core language. So the concept of borrow, when you specify in the arguments, means that this is going to be an immutable reference. In out means that it's a mutable reference. On allows for optimization. So one big difference between Mojo and Python is that Python is interpreted. So you know everything at runtime, which is highly inefficient. But Mojo is compiled. So it does data flow analysis, and by data flow analysis can do optimizations on your code. Even Mojo has an interpreter, but even that is compiled, as far as I understand, is compiled on the spot. So they know if a variable is not copied, I mean, they're going to move it if it is not used outside, depending on the lifetime of the data flow analysis. It can be on, could be that it's moved or it is copied. Copied is less efficient, so they're going to try to move it. So ref is also allowing for optimizations. If you don't modify it, then it's going to be an immutable reference borrowed. But if you modify it inside the function, it's going to be a mutable reference, which is less efficient. Okay, so they also have this operator. It behaves somewhat like standard move in C++. It basically saying, okay, I don't own this string anymore. So if you try to use it later, you're gonna get a compilation error. Okay, so here's an example. You declare this variable, you use it for the last time, and using data flow analysis, it realizes that it's not gonna use anymore, so it destroyed it. So this Mojo has as soon as possible destruction, unlike the in C++ that you have write. In write, you destroy it at the end of the scope, and in cases like tail recursion, this is more efficient. So he knows when he can destroy this, and that's more efficient. Okay. Also, as mentioned before, unsafe pointers are provided, but I like the choice of the name because it discourages from using it. Unsafe pointers, as you can imagine, are unsafe, but many of these main constructs are safer. Okay. As I mentioned, they have traits. They're like Java interface concepts. Replaces the runtime dispatch, useful for metaprogramming. And you can see an example in here. This is the decorator to create the donder methods like move, copy, and constructor for the class. Okay, so you have both of them are taking this trait of quackable. So they must have this quack method. So then I use a parameterization, like a template, metaprogramming, and take another function that takes takes any object that implements that trait in particular. There is a type, any type, that implements that trait. So because of it, I can call quack. But a Mojo, and you can see in here, I call this function with a dog, with us, and it's gonna call this quack. Okay, so if a structure has the function for example, I'm calling this function on a structure that doesn't have that trait, but I try to call it with the same method. But if the function Mojo knows, okay, if this function structure have the method of the trait, I'm gonna let it go as long as it meets the trait. And it's very convenient for programming. You don't have to modify a bunch of places when you want to for that. Okay. So you can have trait of traits. For example, in this case, you have a bird that is an animal, and an animal makes a sound, and a bird can fly. So if you take the trait of bird, you have to fly and also make a sound. So they accumulate the methods. So you can, and also, for example, a trait can have a multiple traits, and also the structures can have multiple traits. It's like multiple inheritance in C++. So here are some of the traits that Mojo has. And finally, metaprogramming, in the manual, the user manual says, to support modular work in AI, Mojo aims to provide a powerful, easy-to-use metaprogramming with zero runtime cost. And yeah, basically, metaprogramming is, you can see of parameterization as something that is done at compile time. And they have this decorator parameter that evaluates an expression at compile time, and I guess they error out if they are not able to do so. And you can see it in here. So I have this parameter, integer. So when I call it with 3, this is going to be called 3 times, which is equivalent to calling this print 3 times in here. So this another, you can see the SIMD type that we saw earlier. You can see how it has a type, D type, and also the size. And the methods are implemented accordingly. Okay, that's all for the video. Thank you for watching.